Hi everybody, welcome to our lab 8. Welcome back, right? So that's the last problem of the guided activity. And I think it's kind of a cool, interesting one. So let's go through it. Joshua Aronson has done extensive work on what he refers to as stereotype threat, which refers to the fact that members of stereotyped groups often feel extra pressure in situations where their behavior confirm the negative reputation that their group lacks a valued ability. Stereotype threat is hypothesized to affect performance, generally by lowering it from what it would have been had the individual not felt threatened. Considerable work has been done with ethnic groups who are stereotypically reputed to do poorly in some area. But Aronson went a step further to ask if stereotype threat could actually lower performance of white males, a group that is normally not associated with a stereotype threat. All right, so their question had to do with whether stereotype threat could kind of acutely affect performance in a group of people that do not suffer historically from a particular stereotype. And how powerful is this thing? Right, and how quickly could we generate some effect? So Aronson et al., 1998, used two independent group of college students. As a statistician, you're like, oh, independent, who were known to excel in mathematics, and for whom doing well in math was considered important. They assigned 11 students to a control group that was simply asked to complete a difficult mathematics exam. They assigned 12 students to a threat condition in which they were told that Asian students typically did better than other students in math tests, and that the purpose of the exam was to help the experimenter understand why this difference exists. Aronson reasoned that simply telling white students that Asian did better on math tests would result in stereotype threat and diminish the students' performance. Let's look at the data and see what happened. So first, let's load the data ST, stereotype threat. It's right here. We can see it has 23 observations and 3 variables, the ID, the score, and we do have 2 different groups, control and threat. Again, you could see it from here too. If you so wished. To see the whole thing, though, you have to flip around instead of scroll. Question 4 for you. What kind of statistical test would be appropriate for answering this question this time? Let's go to question while you think. If you're thinking independent t-test, you are right because we have, in this case, 2 independent groups of people, right? We want to determine if the average score of white males in a threat condition differs from the score of white males, a different set of white males, under a control no threat condition. So actually we have a group that was exposed to the threat condition and a different group, whole different group, not same people, exposed to a non-threat condition. So before we can move on and get our feet dirty in actually running the analysis, we need to check assumptions for independent t-tests. We have 4 in this case. Is the data numerical? Yep, we have a numerical variable. Are the observations independent? Yep, there was random sampling and actually random assignment into the 2 groups, and it's less than 10% of the population size for sure. Weight, I'm affirming here, weight is approximately normally distributed in each of the groups. When it's 2 different groups, you need to test for each independent groups what happens. And I'm asking you to see support below, because when you're doing your independent activity, I want you to state those assumptions and then show how you got to them. And number 4, for independent t-tests, we need to guarantee, or at least to know, whether we can assume equal variances between groups or whether we need to correct for differences in variance between groups. So I'll teach you how to check for this one in a bit. So let's first support the distribution, number 3. For independent t-tests, you need to assess the distribution of scores in each group separately. In the present example, we're comparing participants' score in the threat condition and in the control groups separately. So I'm first using my filter function to create a data set called control group and a data set called threat group. And then I'm getting the range of performance scores for both the control and threat group, which I need to set up my bins. So let's look here. Control group is created here and threat group are created here. So this is the output for these two things. And then I'm also observing the range 4 to 13 for the control group in terms of performance, and for the threat group 0 to 10. So now let me create the histogram. Here's the histogram for the control group. So I have the control group as the data set, and I want to look at score. And I also have a data set for the threat group. And I changed the title depending on which group I have here. And I'm also asking for descriptors so that I can see the difference between mean and median and also the skewness value. Let's run again. Doesn't look great because, you know, it's very small size, so I would not count on the histograms too much. I would go ahead and look at differences between mean and median for each group, and it's not bad at all for the control group. Let's look at skewness and kurtosis, not bad at all. Now again here, mean and median, pretty close, and if you look at skewness, it's doing really well, and also kurtosis. So we are good to go. Homogeneity of variance. That's the assumption that I'm assuming here. I'm saying I can assume that there is no difference in the variability between the two groups, and we can test that explicitly using what's called a Levene's test, and it's testing the following hypothesis. Null hypothesis, variance in the control group is equal to the variance in the experimental group. The alternative hypothesis is that the variance in the control group is different from the variance in the experimental group. And when I run the test, I can see that the p-value is greater than 0.5, which means I should not reject the null hypothesis because the difference between groups and variance is quite likely to occur under the hypothesis that they are equal. So I'll fail to reject the null, that's the decision, and I'll assume that there is equal variance between the groups. Okay? So here's, if the p-value is more than 0.05, as usual, I keep the null hypothesis. If the p-value is less than 0.05, I go with the alternative hypothesis. So this time I went with the null, I failed to reject the null, and I assume equal variance between groups. All right, so I meet the assumptions for the t-test, and I know that I'm going to have to do something to assume that the variance can be assumed to be equal. Now, let's create a table of performance by group. You know how to do that from Lab 4, and I refreshed your memory just up there. So let's grab the code that we need to modify here. Where did we create the table? Let's go there. Here we created the table. Oh, right there. Let's copy and paste this code here and bring it down there. Right here. Now, let's not call it weight data because it's not weight data, it's performance data. And of course, the data set that I want R to open is not the family therapy data, it's the serotype threat data. And I want to group by group. I want the control and experimental groups. Remember, you cannot use lowercase. You have to use exactly the same spelling. And then I pipe again, and then I ask for the mean, not weight, the mean, score, and that's upper caps here, so I better do the same here and here as well. R is nice because it gives us here the hints. And then I want R to show me not the weight data, but the performance data. There you go. We can see that under the control condition of no threat, the white males in that group had a performance score of 9.63, and the white males in the threat group had a performance score of 6.58. So there is a difference there. That can also be illustrated in the bar plot, which if I didn't have this here, you could come here and copy and paste from here and do the necessary modifications. So you can go through that plot and figure out what you need to change. And if you can't figure that out, you need to go back to Lab 4. And if you can't figure it out there, you need to come to our live session Wednesday, or you should set up time with me or Dalton to figure this out, because I'll ask you to copy and paste stuff and modify for your independent activity. So here is the data set that I want. X, I have group. Y, I have score. Pretty much everything here the same. I'm just changing title, label of the x-axis, label of the y-axis. I am making the thing not float above the x-axis. And again, I highly recommend that if something goes off, you do not use this thing, right? So you can delete that plus and comment this out. And just let R select for you the scale. And then just change this if you feel it's necessary. In this case, it's very evident the difference. We don't need to do much in terms of refixing the scaling to kind of demonstrate the difference that we're seeing. Now, descriptive statistics shows us that participants who experienced stereotype threat demonstrated reduced performance. But what the descriptive statistics cannot tell us is whether this difference in performance between the two groups is likely to happen by chance alone due to sampling error. Let's find out using hypothesis test. In this case, an independent t-test. So I will break here and we'll continue on the next video, because otherwise we'll cut this in the middle of hypothesis testing. All right, so we'll see you then in a bit.